In many settings, we need to take our tools here. So additive rule, inclusion, exclusion, product or multiplicative rule. We need to take those tools and we need to combine them and use multiple of those tools in order to solve a problem. So let's do an example of that. We're going to do a couple more problems where we're counting strings of a certain length on an alphabet. So we want to study the set of strings of length 5 on the alphabet with 4 characters A, B, C, D. So just to give an example here, here's a few strings of length 5 on this alphabet. So they're just words with 4 possible characters in each of 5 places. And when I say words, I literally mean just sequences of letters. They don't have to be real words. So there's a few strings of length 5 on this alphabet. So I want to know about the size of some subsets of this set. So here's our first question. How many strings of length 5 here start with the sequence CAB or end with the sequence AB or both? So to give kind of some intuitive thinking here, for the first set, I'm going to call this set A. So this is the set of all strings that start with CAB. And I'll call this set B, the set of strings that end with AB. Okay, so let's try to see if we can figure out the size of set A. So if I think about set A, I have the CAB. That's fixed. Everything in set A begins with CAB. And then I'm going to have 2 more slots. And in these slots, I can put whatever I want from this alphabet here. That means that I can treat this essentially as a problem of finding the size of the set of all strings of length 2, just in these little slots here. I need to fill these in. There's 4 ways to fill in the first one. There's 4 ways to fill in the second one. I'm in a setting of sequential choice, so I'm going to use my multiplicative principle. So by the multiplicative or product rule, the size of A is equal to 4 squared, or 16, because I have 4 choices in each of 2 free slots. Okay, but what about B? For B, we can do something pretty similar, actually. So for B, I need things to end with AB, and I have 3 open slots before. So I can do the same kind of reasoning. Similarly, the size of B is equal to 4 cubed, which is 64. So here's the thing, though. I can't yet just add these together. I can't add 16 and 64 and get 80, because I need to check for the intersection. I'm not sure if I'm doing a disjoint union problem or not. So let's check A intersect B. So A intersect B, what is that set? Well, I have to have strings that begin with the 3 letters CAB and end with the 2 letters AB. And the only way for me to make that work is to put the 2 letters AB right here. So I would have to fill in A and B right there in order to make that work. I have no more choices left. My string is determined. And so that means that the set A intersect B is just the set containing the single string CAB AB. I guess kebab is how you would pronounce that. There's just one string in there, and so that means that the size of this intersection is equal to 1. So by inclusion exclusion, which I'll abbreviate IE, our final count is, let's check here. So the size of A union B. So I'm caring about the size of A union B because I'm doing an OR problem. Size of A union B is equal to 16, that's the size of A, plus 64, that's the size of B, minus 1, that's the size of the intersection, which is equal to 79. So that's my final result. Let's do another example. This time, the question I'm going to ask is how many of these strings of length 5 on the alphabet A, B, C, D contain the substring BAD or bad? So a few examples of the kinds of strings that I'm looking for. BADAC, that contains the string bad. CBADD contains the string bad, and also here's another one, DCBAD. These all contain the string BAD consecutively. So how am I going to count this? This is going to actually bring me to both an application of disjoint choice. So the reason I use disjoint choice here is if I look at these examples, hey, BAD starts with B, and I have 3 disjoint possibilities of where to put the B. I could put the B at the beginning, I could put it in the second slot, or I could put it in the third slot. I can't put it any later than the third slot because then the A and the D wouldn't fit in a string of length 5. So I have 3 disjoint choices of where to put the B. Where am I going to put the B? I have 3 disjoint choices. I'm going to use the addition principle. So here's the thing. Let's go ahead and log that. I'll use the addition principle for each of the 3 disjoint possible locations of the B. Okay, so for each of those locations, okay, if I think about where to put the B, so let's imagine I put the B in the first slot, for example, that means my filling in problem looks like this. I have 2 more free slots because the A and the D are determined. I have 2 more free slots here. And so I have 16, 4 squared, possible choices if I decide to put the B at the beginning. So I'm going to have 4 squared equals 16 choices of how to fill in those remaining letters. This is also going to work no matter where else I put the B. So no matter where I put the B, I'm going to put the A and the D right after, and I'm going to have 2 more slots to fill in. So this means that for each possibility, there are 4 squared, or 16, possible strings by the multiplicative principle, or product principle. So, using the addition principle, we're going to say, hey, I have 16 possibilities if I put the B at the very beginning, 16 more if I put it in the second slot, 16 more if I put it in the third slot, which is 48, and that's my final answer. So to get here to my final answer in both of these problems, I had to use some combination of the product principle, inclusion, exclusion, and the addition principle.